All right, and our next topic today is going to be about the Vsepr theory. Vsepr stands for valence shell electron pair repulsion theory. You don't really need to know that, you just need to know that that's what we use to accomplish our learning goal. So by the end of today, you should be able to predict the shape of simple molecules using this Vsepr theory. So first off, electron pairs. Okay. An electron pair are those electrons that share the same orbital. So again, they're in the same orbital, and the reason why they're okay with that is because they have opposite spins. So that's what makes them stable. Lone pairs are negatively charged, so they repel, just like we've always learned. And so what we're going to do is we're going to draw them in a three-dimensional way such that this repulsion is at a minimum and they're the most stable. Electron pairs can be shown three ways. We can use electrons with arrows going up and down to show opposite spins. We can use two dots, which you can see over here in some of my examples. And we can also use just a straight line. Okay? So all of those symbols represent electron pairs for this course. So the Vsepr theory uses electron pairs to predict the three-dimensional shape of a molecule. So there are some key components here. We have to remember that electron pairs repel and want to stay as far away from each other as possible. And terminal atoms, so those are the atoms that are attached to the central atom, they move as far away as possible from each other to again minimize the electron repulsion. Alright, so when we're doing this, we have a number of steps that we need to look at to figure out the shape of the Vsepr, or the Vsepr shape of the molecule. So step one, we count the number of bonds around the central atom. Treat double and triple bonds as single bonds. This is very similar to what you guys did to figure out the hybridization of a particular atom. Then you count the number of lone pairs around the central atom and add them together to get the total number of charge clouds. Charge clouds is a term that you'll probably see in some textbooks and online. It's the same as saying an electron cloud or an orbital. We sort of use them interchangeably. Once you have the total number of charge clouds, you're going to do step two, predict the shape based on the total number of charge clouds. Look at the electron pair arrangement, which includes all pairs, bonding, and, this should say lone pairs. Or you could also give me the molecular shape, which includes only bonding pairs. Okay, so if I ask you for the electron pair arrangement, you have to include all pairs, bonding and lone pairs. Pairs. Yeah, forget it. Pairs, there we go. If I ask you for just the molecular shape, that just includes the bonding pairs. Alright, so you guys are going to, in class, get a big, huge sheet with a bunch of different Vsepr shapes. So don't worry about memorizing all of this right now. We're going to work on that together in class. So here are some examples of different Vsepr shapes, okay? If you have two charge clouds, and both of those charge clouds actually form bonds, that means you have no lone pairs, and your sort of general formula is AX2. So you've got a central atom and two terminal atoms attached to it. Your shape is going to be linear. So this is where, if we look at our learning goal, to predict the shape of simple molecules using the Vsepr theory, that's this. Okay? If you have three charge clouds with three bonds and no lone pairs, you get a trigonal planar. If you've got three charge clouds with two bonds and one lone pair, you get a bent shape. So, okay, great, miss. That's so helpful. Let's actually go through some examples to see what they look like. So the first example there is an AX2. So an example of that is carbon dioxide, CO2. This is going to end up being linear according to that little chart on the last page. Why? Okay, basically because of the way the hybrid orbitals work and the overlapping of the pi orbitals, we end up with, here's one charge cloud, here's two charge clouds, we have no lone pairs on the carbon, it's going to be 180 degrees, so we call that linear. Here's an example of an AX3 or a trigonal planar shape. So the example is boron trifluoride. Again, this is an incomplete octet. How does it work? Well, we've got some hybridized orbitals. Your bond angle ends up being 120 degrees. So if you have a central atom with 3 things attached to it and no lone pairs, that's called trigonal planar. If you have something like SO2, which has a central atom with only 2 things attached to it, and you end up with a lone pair, well, this isn't trigonal planar anymore, even though there are technically 3 areas where electrons are present. Okay? The shape of it, the molecular shape, is called bent, because the shape just looks like this, right? We don't actually see those electrons because they're way too small. So that looks more like a bent shape. Okay? If we had something else attached to it, that would be a trigonal planar. So the the electron geometry for this molecule is trigonal planar, but the molecular geometry is bent. All right, we're going to go through charge clouds, or examples with 4 charge clouds. You have 3 possible shapes going on here. You can have a tetrahedral shape, a trigonal pyramidal shape, sometimes it's called trigonal bipyramidal, I'll accept both, and a bent shape. So what do each of those look like? Well, the first one, methane. What's your formula for methane? Hopefully you guys all know. CH4. So in this case, I've got one central atom, my carbon in the middle here, and it's bonded to 4 hydrogens, no lone pairs. So, 4 bonds, no lone pairs, tetrahedral. Here is an example of something with 4 charge clouds, but only 3 things bonded to it. So ammonia is NH3. So I've got nitrogen in the middle bonded to 3 hydrogens. And when we actually draw out the Lewis dot structure, we've got an extra lone pair of electrons that could form a coordinate covalent bond. Kind of jog your memory there. But the shape of this, because we don't count this extra cloud as a shape, when we just look at the atoms, they kind of look like this. And so we call that trigonal pyramidal. If we have something like water, H2O, we still have 4 charge clouds, because we've got one here, one here, one here, one here. But in this case, what's happening is we only have 2 atoms attached to your central. So when we were to draw it out, it would look like this. And we don't, again, take into account this when we're talking about the molecular shape. So this is also bent. All right. Now examples with 5 charge clouds. You have 4 possible different shapes. So you've got 5 bonds, no lone pairs, gives you trigonal bipyramidal. 4 bonds with 1 lone pair gives you a seesaw shape. 3 bonds, 2 lone pairs gives you T-shape. And 2 bonds, 3 lone pairs gives you linear. So the first example, trigonal bipyramidal. It's sort of hard to see in these diagrams, the 3D shape of these molecules. We are going to build them in class so that you can get a good idea. But again, all that's happening here is we're trying to get these chlorines as far apart from each other as we possibly can. And that's what's happening in all of these examples. Okay, so the ideal angles in this case, we have these 3 at 90-degree angles to each other, and then in here we have angles of 120 degrees. That's called trigonal bipyramidal. If we take away one of these chlorines and just have an extra charge cloud, so instead of having 5 things attached to your sulfur, in this case we have 4 fluorines and an extra lone pair, this is what's called a seesaw shape. If we have 3 things attached to your central atom and 2 extra charge clouds, 2 extra lone pairs, this is called T-shaped. And if we have only 2 things attached and 3 extra charge clouds, this is, again, linear. Last ones we're going to look at are the examples with 6 charge clouds. So we've got lots of different options here. We can have 6 bonds with no lone pairs. That gives you octahedral. 5 bonds and 1 lone pair is square pyramidal. 4 bonds and 2 lone pairs is square planar. So again, here's octahedral. Okay? 1, 2, 3, 4, 5, 6 things attached to your central atom. Here again we have 6 things attached to your central atom, but 1 is a lone pair. So this is called square pyramidal because you've sort of got a flat square here in this X and 1 sticking up. This is called square planar. Again, we have 6 things attached to your central atom, but 2 of them are non-bonding pairs. So I've got 1 fluorine, 2, 3, 4. They're going to sort of sit flat in a square, so we call them square planars. And those are sort of the ones. Then we also have a T-shape and a linear, but we'll go through those in class. All right, bond angles for tetrahedral molecules. You can see in all of these, the angles are really close together. Okay, they're all hovering around the 108, 109, 110 mark, okay? Why is this the case? Because the lone pair repels the bonding pairs. So these 2 extra electrons here are negatively charged. They're going to push down those other, in this case, hydrogen atoms. Okay? The more lone pairs you have up here, the more pushing down is going to happen, and therefore the smaller your angle is going to be. So here's an example. I've got 2 lone pairs here. 1 here and 1 here. So because I've got that extra bit of negative happening, we're going to push this way even more and make this angle in here a little bit smaller. So you can see on the last slide it was around 107. Here we've got 104.5. Again, here is where an 110 degree comes in. This is carbon with 3 hydrogens and a chlorine attached to it. Okay, what's going to happen here? The chlorine is very, very electronegative, and it's going to attract the electrons that are hanging out in this bond. That's what we learned in grade 11. So when that happens, if those electrons are being pulled towards the chlorine, that gives all the electrons here a little bit more room to move around. That makes our angle a little bit bigger. I guess that's it. I've got a video to show you. I'll do that in class, and we'll work on some of these questions together.